functions. So first-class functions are these black boxes, and you put inputs in and you get outputs out, and you use them to describe infinite behavior. And the interesting thing is that the only way to use a function is to apply it to a value. And the other core aspect is programming with algebraic data types. And they are these tree-shaped things, and you use them to encode finite information, and you know the structure. And when you want to use them, then you traverse the structure. And the classic work on comparing these two things is Reynolds defunctionalization, which I think came up yesterday here at the conference. And the idea there is to take a program written with first-class functions, and then you do a whole program transformation into a program that's only using data types, and there are no first-class functions left. And Reynolds did that in order to understand the program better. So he wrote an interpreter in a higher-order language, and then he transformed it, and then, for example, the data type of closures kind of popped up out of the transformation. And that's also one thing we want to do. But defunctionalization is also used in compilers because most machines, they support data better than codata or than functions. So you use defunctionalization somewhere in your compiler. That's one thing to do. Now, there is a problem with this picture, which is that defunctionalization does not actually reach all programs that we could write with data types. So there are actually much more programs that are not in the image of defunctionalization. And that's a problem because it would be nice to do the opposite of defunctionalization, which is called refunctionalization, and has, for example, been explored by Olivier Donvy. And this only works if we happen to be in the image of defunctionalization. So there are a bunch of papers out there that somewhere in the middle say, oh, this program in figure 7 happens to be in defunctionalized form, so we can refunctionalize it. But what we want to have is a situation where every program that uses data types, you can refunctionalize and end up with a different program. And the way we do that is that we generalize from first-class functions to arbitrary codata types. Also like several other talks we have seen at this conference. But we do it, well, slightly differently. So what we present today is two language fragments that are very symmetric in the sense that we can de- and refunctionalize back and forth. So we start with the data language, which is entirely boring. So we have data type declarations. They look like JEDITs or something, but they are not, because there is not even polymorphism in this language. So a data type is defined by listing the constructors of the data type. And then we can have functions, which are defined by giving multiple equations that use pattern matching to decide what to do. And actually, they are only allowed to pattern match on the first argument right now. So if you want to pattern match on later arguments, you need to write a helper function. Okay, now we have a second language that uses codata types, and then it looks like this. So we have codata type declarations, and in order to define a codata type, you need to give the type signatures of all your destructors, and then you can write functions, and you do that by giving multiple equations, and they use copattern matching. So we can read this lower line as when you want to repeat a number, then you get a stream, and when you later call the observation tail on that stream, then it's again the repeated number. So this dot tail means when you later call tail. So in our language, we don't actually have first-class functions. We have only codata types. We want to generalize from first-class functions to codata types. And the way to do that is to write a codata type for functions. And this works because the only observation for functions is application, and application takes an argument. So our observations can take arguments directly. And this allows us to write functions as a user-defined type. And then we can, for example, map over a stream. And let's look at this first equation. So we can read this as when you map the function f over a stream S, and later want to inspect the head of the stream, then that's the same thing as inspecting the head of the original stream, but you also need to inspect what the function does when applied to that value. So that's how you program in this language. And as you can see, you can do the usual functional programming. And now the good thing is that we have de- and refunctionalization that works both ways. And the way it works is by converting codata types to data types. And so you can read this in both directions, depending on what you want to de- or refunctionalize. So it will change between destructors and functions that do pattern matching, and functions that do copattern matching and constructors. So let's look at a little example. This is the addition function I think we saw on the slide about the data language in the upper code snippet, and then the lower code snippet, it's the refunctionalized version of it. So we can see that the data type nut becomes the co-data type nut, and that the constructors of the data type become functions in the co-data formulation. So we kind of just copy down the signatures. Then we see that the function in the data formulation becomes a destructor in the co-data formulation. So here we also need to put a dot somewhere, but that's only a surface syntax change. That's not, well, it's isomorphic. It's just putting a dot and moving a nut somewhere else. Yes, which we see here. And then we copy down the equations. And we also need to put some dots. So the interesting thing is that the two equations in the yellow fragment in the data language, they are together in one function. But in the co-data language, they are in two different functions. So we change where it's the same equations, which pretty clearly shows that programs have the same dynamic semantics. But the equations are at different places in the program, which will become important soon. Okay. So D and refunctionalization, they keep working, and actually they work better, because this problem that there are programs that are not in defunctionalized form doesn't exist anymore. This works for all programs in the languages that I defined here. Why exactly is that? So it's because of mostly the first item here. So this fully automatic refunctionalization that always works. We can achieve that first because instead of functions, we have co-data types with multiple observations that take arguments. And this allows us to refunctionalize a program where we have a data type with multiple functions that pattern match on it. So that's the case which is usually not supported. So if you have multiple functions that pattern match on it, pattern match on the same data type, this will become multiple destructors of the co-data type, which works just fine. But if you would want to refunctionalize to a function, then functions only support apply. So we wouldn't know what to do with the other function. We also in our language only support top-level first-order functions, and we use copatterns instead of some kind of co-case construct or something. And this makes everything simpler. So this allows us to not do lambda lifting because it's kind of already lambda lifted, and we don't need to do any name mangling, which makes it easier to round trip the functions. But you could imagine to just add that kind of, and then you need to store the name that something had in order to create it again. So I guess that's all feasible, but it's not our focus here. Okay. But I believe the co-data thing is essential. It's essential to support multiple observations. So we tried this out with the original case study of the paper by Reynolds, which was a meta-circular interpreter. So we translated that in our co-data language, and then we defunctionalized it. Okay, so here's just a little snippet of it. So it's the declaration for the co-data type of values, and values just support one observation, which applies a value and to get yet another value. So here we see that we are dealing with a lambda calculus. So that's the domain equation if you want. And then one of the functions that comes up is a function to create a closure based on an expression and an environment. So this one doesn't actually show up literally in Reynolds code, but it's one of these helper functions we have to introduce because we in order to get it into this form where we either do pattern matching or co-pattern matching. Now, if we defunctionalize this, then where we still have a type of values, it just becomes a data type. We have the structure becomes a function, and the function becomes a constructor. And now we see that values are actually stored as closures, which is the kind of goal, one of the goals of defunctionalization, to see the data layout more clearly. And then we went beyond a Reynolds example, and we changed the code. So we changed the code in both editions in order to add normalization by evaluation, which is one way to extend an interpreter. It's like when you have an interpreter, the next thing you can do is normalization by evaluation. And there are two changes you need to do. And the first change is to add a way to refi values to expressions. So you have a value and you want to get back an expression. And in the co-data fragment, that means adding a destructor for values. And then that means in the data fragment, we add a function that pattern matches on values and returns. So these types look wrong to me. So they should return expressions, not values. Okay. So the interesting thing is that in the co-data language, we need to change a type, but in the data language, we just add a function. But if you want to actually implement reification, then you also need to add some form of symbolic execution. So you have residual variables and residual applications, which are little pieces of syntax that need to live in your value space. And in order to add them, in the Codata language, we just add a bunch of functions. But in the data language, we need to add constructors to an existing data type. So these are the two changes we need to do. And they are differently modular in these two different representations. Okay? Because adding functions is very modular. We can do that in a different file. But adding something to an existing type is usually not supported, or it's harder to support by a language. So the interesting thing is that different changes are modular in the different representations. And that sounds very much like the expression problem. Yes? So this sounds very much like the expression problem. So in order to make that more clear, we noted that we can write down our programs as matrices, just so. So we just replace a bunch of new lines by correct number of spaces. That doesn't change the language at all, because it's carefully set up to pass anyway. And we can write down these matrices. So the upper thing is the data version of the addition function we saw earlier, and the lower thing is the Codata version. It's the same code as on the previous slide. And we can zoom in a little bit by throwing out a bunch of boring stuff. So it turns out that in the body of the matrix, we have the equations. And the left-hand sides of the equations, they are determined by in which cell we are in. Okay? Because we always just know that, so from the left, from the columns, we know which function we are currently defining. And from the top, we know what we are currently pattern matching or co-pattern matching on. So let's throw this away, okay, and zoom in. We also need to kind of have a naming scheme for the variables, because we don't have binding forms anymore, but we know how many variables we have, because again, that's because we are in a certain location. So we just call it x1, x2, and so on. And yes, so now maybe it's more readable. And we see that these are the two programs, okay? And now there are two interesting things. One interesting thing is it's modular to add rows, and it's not modular to add columns, because adding rows means adding top-level declarations, okay? And the other thing is that defunctionalization and refunctionalization now correspond directly to a matrix transposition. Okay, that means that it's clear that they are inverse to each other, because they are both matrix transposition, and matrix transposition is self-inverse. And it also makes it clear the connection to the expression problem, because if you draw a picture about the expression problem, you also draw a matrix like this. And then you say, oh, we want to extend in that direction and in that direction. And here we would say that we can only extend in that direction, but we can transpose the matrix, and then that direction actually is the other direction. Okay? So I mean, this doesn't solve the expression problem, because you still need to do this whole program transformation. But maybe this explains what's hard about the expression problem. It's that there is this whole program transformation hidden in there, which we would like to avoid. Well, in some solutions would like to avoid it. Or maybe it's just not a problem. Maybe we can have an IDE where you program in one style, and then you press a button, and it's turned into the other style, and the IDE just does the whole program transformation, and then you change it a little bit, and you press the other button, and you're back in the other style. Which is only possible if refunctionalization is actually automatic. So you don't want to get an error message, oh no, after you change, you're no longer in a defunctionalized form. Okay. So programs can be written as matrices, and D in refunctionalization is matrix transposition. We have modular extension only in one direction. And therefore, D in refunctionalization changes the dimension of modularly supported extensibility. And if you think about all the solutions of the expression problem you probably know, many of them are actually based on defunctionalization and refunctionalization. They somehow encode the data type using some kind of visitor church encoding thingy, which ends up using a record, which is just refunctionalization. Okay? So the papers don't say that, but I think they already use that insight. So in our paper, we have a bunch of more examples. We have formalized lots of things, and we have the source code of this case study with the normalization by evaluation. The formalization is completely straightforward because we just set everything up so that it just works. So the key is really, so the key is in the language design. There's no interesting proof in a way. The proof is all just induction, and you do the usual lemmas, and you do more induction when you're done. So there is, so this whole thing with the dots kind of begs the question, what's the relation to object-oriented programming? And I learned that we are against OOP in the last talk. Okay, so my take on this is let's steal something from them. Okay, let's steal the good things. So object-oriented programming is this like co-data plus implicit self-recursion plus mutable state plus a lot of things. And the traditional way of doing functional programming is you have data in first-class functions. And maybe people here find that better. But what I want to propose here is this metric style of doing functional programming, where you have data and co-data and first-order functions. So it's kind of a step back from first-class to first-order functions. So they both start with first, but first-order functions, they are like the non-higher-order ones. But we do have co-data instead, and we can use co-data to encode our nice higher-order functions and more because we have the multiple observations. So I'm really interested in exploring this more, like from an engineering point of view. What kind of programs can we write? I mean, there are lots of papers exploring this from a type theory point of view, like how can we ensure termination and what kind of proofs can we have and what kind of things are true or not. So that's not the take I'm taking on this. That's why in our language we just have recursion of the top-level statements and it's just simply typed and so on. And we're more interested in writing programs. Because already the traditional FP can be really good for writing programs and is often or maybe always better than the object-oriented way. And I hope that it can become even better. Okay, to conclude, we generalize from first-class functions to co-data types with multiple observations that can take arguments, which gives us automatic defunctionalization and refunctionalization. And these two things are actually matrix transpositions, and they switch the dimension of extensibility. And this kind of thing allows us to study, or steal and then study one little thing from object-oriented thinking in a functional programming setting. Thank you.
I can't help feeling that you've pulled a bit of a fast one with the data and co-data thing. These functionalization and refunctionalization go backwards and forwards, but co-data types contain co-data which might be infinite, whereas the data types only contain finite things. So where did that go?
Okay, so the question is, where are the finite things in the co-data? And the answer is, well, they are in the co-data.
No, that's not the question. Is where are the infinite things in the data?
I'm confused.
So co-data types contain the finite and the infinite structures. So a co-data type of lists with a nil and the cons, or the head and a tail. Well, if you have a head and a tail and a possibly nil, then you have the finite things as well. A co-data type of streams has only infinite things, but a co-data type of lists has the finite and the infinite lists.
So I'm confused. What's a co-data type of lists anyway? I mean, so the co-data type for streams I presented, it has only infinite structures because you can always call tail.
Yep.
And if I would write down a data type for lists, then it would have only finite structures because it's a call-by-value language, and so you can only build up a finite structure. So if you want to have a terminable stream, then the tail thing would return maybe or something, but maybe is a data type. Okay? So there's your little bit of finiteness in the streams. Does that answer help?
But the stream might be infinite. You can't turn that back into a data type again.
So you mean what's the intuition for having defunctionalization and refunctionalization do that? Okay. So my intuition is that if a program, so my intuition is that data types, they are finite descriptions of something, and co-data types, they are infinite behavior. And now we can describe infinite behavior in a finite way. Okay, so we can take, or we can go both ways. So maybe the other way is easier. So we can start with a finite description like a lambda term, and we turn this into an infinite behavior like an infinitely running function. But we can also go the other way. We can also take an infinite behavior and describe it finitely. And there is no need for the description to be infinite just because the behavior is. Otherwise, we couldn't program. Which is the cool thing, isn't it? And we can do that automatically, always.
I'll call you afterwards.
So just to mention of some related work, Bob Harper in his textbook has a chapter on OOP, which characterizes. Which talks specifically about a, quote, a dispatch matrix and uses the word transposition to talk about the relationship between class-based and method-based And so I'm wondering, A, if you're familiar with that, and if it seems very similar to the characterization you're giving here. I don't think he talks about defunctionalization explicitly, but I'm wondering, yeah, what's the relationship, and if there's what specifically the advance is? If you're aware of it. If you're not aware of it, then.
No, I'm somewhat aware of the book, but I'm not sure I'm aware of that particular chapter. I guess not.
It's okay.
But it sounds like
it's very related. It's related work.
So dispatch metrics sounds good.
It's
that's a good name for our metrics.
Yes.
We'll let you guys talk about it offline. Let's thank Tilman again. Thank you. So we have a break now, and we'll start again at 4:50.